I've worked mainly in the industrial automation area, but of course, naturally, electrical engineering is a key part of the business. And I'm just going to do a quick run through on the very interesting high voltage standard, which has its antecedents or based from the IEC, International Electric Technical Commission, but it is an Australian standard. So just to give you a quick run through on the HV design standard, AS 2067-2008, which of course has been a few minor changes since. In fact, there's a review committee going through at the moment. So it's AS 2067, focusing on substations, high voltage installations exceeding 1,000 volts AC. Okay, so off we go. As I say, I'm just going to do this in a very quick fashion. You'll get a full set of slides, so you don't need to listen to my voice, and hopefully you can get some value out of this presentation. So it refers to high voltage installations, electrical network substations, and obviously electrical installations associated with power stations. And also high voltage parts of electrical installations are covered in the above. So really mainly electrical installations and perhaps consumer installations as well. And it also refers to mine site installations, except where there's not specific legislation covering that for mine electrical equipment. So just bear in mind that there's also mandatory requirements for Western Australian mine sites as well. It doesn't apply to the following very interesting areas of high voltage, of course, which are overhead lines, underground cables, ship and offshore installations, which is actually quite a big one, especially the amount of offshore activity going on these days. You need to think about oil rigs with the high voltage gas turbine outputs. And then, of course, mine site electrical installations and switchgear transformers and stuff like X-ray equipment where you've got a high voltage operation, but you can't actually access the equipment, and in fact you've got a low voltage feed to it, and obviously test sites as well. Obviously you can't run a test site permanently like the Japanese do with whaling, testing whaling on an ongoing basis, but you're actually capturing them. Test sites obviously for a short duration period, and it's genuinely testing, not operations. So just briefly, there's 2008, there's an amendment in 2010, and there's also a project which commenced in 2012 to focus on earthing, a good old chestnut, and arc flash hazards. And the contents of those 2067 I'm just going to briefly look through now. It goes through all the way from scope and definitions, fundamental requirements, installation coordination, all the way through to safety issues. So I'm just going to quickly look through the various bits. Fundamental requirements, obviously, installations equipment must be capable of withstanding electrical, mechanical, and climatic and environmental impacts. Installation equipment must identify safety requirements, designed and constructed to withstand mechanical thermal effects from short circuits, electrical faults, and obviously structural requirements, and obviously mandatory climatic and environmental requirements, really important. Cover specific primary equipment selection requirements, and this ranges on circuit breakers, disconnectors, power transformers, reactors, CTs, current transformers, PTs, voltage transformers, surge arresters and capacitor banks, and obviously you've got other standards which go into more detail on power transformers, such as AS2374, really important standard, and the 62271, which looks at high voltage switchgear and control gear. And there's also stuff for cables and overhead lines. Installation, general requirements covered here, specific requirements for open type indoor switchboards, and obviously for buildings including prefabricated substations, installations, mast, pole or tower, and things such as operational application of safety clearances, really important. Safety measures obviously contain requirements for protection against direct contact with live parts. Obviously really important to ensure that you do not come anywhere near a live component, either inadvertently or deliberately. And obviously detailed requirements for arc fault, which has become a really interesting area. A lot of work being done there. Lightning, fire, and explosion. So, for example, in a hazardous area environment. Earthing systems, really interesting area. Obviously, you need acceptable safety and to ensure the integrity of the equipment and proximity to the earthing system is maintained. So obviously, earthing is quite a discussion here. I'm not going to go into this. And you can see it on the slides. Safety criteria are very important. Obviously, you want to avoid a ventricular fibrillation. Permissible limits are defined. Big issue with high voltage, of course, is insulation. So there's a lot of discussion there about insulation coordination. Basic impulse level coordination is difficult to inspect. You obviously can't look at insulation very easily and say, look, that's fine. You obviously need some form of testing. And it must be able to withstand lightning and switching impulse levels. We'll talk about the pulse later. Insulation coordination is very important. Basic insulation level, reference insulation level is referred to as an impulse crest with a standard wave not longer than 1.2 microseconds to reach the peak and 50 microseconds to decay to 50% of the peak. This is quite an important definition. There's always a bit of a discussion about this as to other sort of test waveforms which don't match up with that, but that's the requirement. We have to have a standard somewhere. Power frequency test is performed, and there's a diagram here. I'm going to worry about that. Just have a look at power system planning. Again, I just want to point out some of the issues that you need to be aware of here. Planning criteria, load forecasting, voltage selection, site conditions, and security of supply. Really interesting to talk about that. Obviously, nothing's more irritating than losing power, and sometimes it can be absolutely critical that you don't lose power. Planning is very important. As you said, clients often don't know what they want. They need assistance. They may not have high voltage guys in their team. And of course, the engineer is not always aware of the client-specific requirements. And the design often has different rules. Different people do it in different ways. And obviously, you have lots of arguments, reworking, which we all know about with engineering. And inevitably, you get a system which doesn't always meet your expectations. So we've got to try and avoid that. Agree on basic system requirements, get the supply authority involved, and obviously try and avoid cost or time scheduling blowouts. The sooner you agree, better the time wastage, minimal time wastage. So planning criteria relate to safety, which is obviously critical, reliability and flexibility. Load forecasting, very important, voltage selection, power quality. Site conditions, very important. Security of supply and system studies, load flow analysis, fault calculations. System safety, very important. Efficient grounding system, clearance distances, appropriate recloser shots, timings, and fast clearance of faults. And obviously, not to be forgotten, insulation discs, the right number, and the right type on your overhead line insulators. Sometimes they get old and damaged. System safety, appropriate sizing of your lines and cables, enabling switch on to fault, feature on your numerical relays, surge arresters of power transformer bushings, and obviously looking at buses. I'll talk about buses at the end. System flexibility, nothing's more frustrating when you've got a power system and you can't flex it to a new requirement without shutting the whole system down or having to do extensive work. So try and anticipate growth, space in your substations, and space doesn't necessarily mean only physical space, but obviously additional batteries, and obviously area in which to put in extra buses. Enough ampacity, short circuit capability for line conductors, and capacity for transformers to include any possibility, hint of a possible overload. Make sure you've spoken about contractual maximum demand. That's always a very big chestnut for the supply authority. Do a load survey about peak load, maximum demand, diversity factor, load factor. I'll briefly define these in a tick in the next part. Critical load, essential load, general purpose. Constant voltage supply, no sags or surges, and obviously harmonic currents and filtering. Peak load is the maximum load. Average load is averaged over time. Connected load is the sum of all electrical ratings, all loads connected. But that doesn't necessarily mean that you'll be running all those loads simultaneously, hopefully not. And demand is load averaged over a time period in kVA normally, kilovolt amps, typically 30 minutes, so you average it out over 30 minutes. Very important for maximum demand calculation. Maximum demand is the gross all demands that occur during a specific period, and that's what your utility will charge you, or your transmission authority. Load factor is the average load over the peak load. Demand factor, maximum load over connected load. And diversity factor is sum of individual maximum demand over total demand. So demand factor is maximum demand over connected. So for example here, I'm not going to go through these calculations, they're on the slides, but you may have a connected load of 400 kVA, while the maximum demand of 150 kVA may be read from customers' meter at a particular time. So it's 150 kVA maximum demand divided by 400 connected load. As you can see, the connected load is huge, but there's no way that you're going to have everything running at the same time. Diversity factor is another important issue, which is the sum of individual peak demands divided by the peak system demand. And then you've got an example here of demand factor and diversity factor calculations. I'm not going to worry about those. They're very well explained in the slides. Power quality is always an interesting issue. Very frustrating today with all the amount of electronic devices, but you need to make sure that it is top quality. Voltage limits is inevitably a problem. Western Australia, for example, you often have 250 volts. Now we're down to an average of 230 volts, but some remote sites are 250 volts. So again, very important to make sure that we keep the limits. One criteria is often to keep the voltage level a drop to a percentage, but the best thing is to nominate absolute value of voltage at a node. So that's it. Define the voltage limit. So there's a few comments here about voltage level selection. The higher the voltage, the lower the current. That means that you need a smaller conductor. There's lower voltage drop. And obviously too small conductors don't have the physical strength to handle all conditions, so bear that in mind. And higher voltages can be more expensive because of increased insulation requirements. So there is a trade-off. I'm sure there's some program which will give you the optimal selection, will give you guidance. Voltage selection. Site conditions obviously important, which are described here. IP code really important. So for example, you have different choices. IP22 protection gives you, if you look at these charts, gives you protection against insertion of fingers, will not be damaged, become unsafe during specified tests, which is exposed to vertically or nearly vertically dripping water. So that's the IP22, but you can get various combinations depending on the setup there. That's a typical minimum requirement for design of electrical accessories for indoor use. Soil electrical resistivity, very important. I'm not going into that in this section here. The final discussion here before bus structures is system reliability, and obviously there's different ways of interrupting your client. System reliability is really important to have some handle on how your network's performing. Not necessarily for a penalty, but to give the electrical utility an idea of how they're performing reliability. Nothing is more irritating than having your power dropping off all the time. Sometimes there's no choice. You're out in a rural area or there's a lot of lightning or storms. Well, you get what you pay for. So here's a typical example of calculations. I'm not going to worry about these here. They are important for the utility. So security of supply, very important. selecting the voltages, and redundancy or reliability. Protection coordination, simple power station systems, following the good old famous KISS principle, and monitoring control. And there's various busbar configurations which are listed here and discussed here. Single busbar with single breaker, pros and cons. Double busbar with single breaker. Double busbar with double breakers. Large switching stations, a lot better option. Most distribution systems use a main and transfer bus, as we've got over here. One breaker serves each circuit. Circuits normally connected to a main bus can be transferred to a transfer bus using a bus tieback over here. And the transfer bus is standby for emergency purposes. Circuits on the transfer bus are not protected by breakers. So very important to know that. Breaker and a half is the final solution there. And then the famous ring busbar, which is one breaker per circuit, as you can see. Ring, very good, high reliability, obviously quite appealing in an urban environment. Perhaps got to 5 circuits. Beyond then it becomes a bit more tricky with a ring busbar. Protecting relaying is very complex, I must say. Something I look at a bit of horror. Okay, that's all from me. That's a presentation on the AS2067 standard. Thank you very much for tuning into this and listening to this. The slides are all detailed. You should have a full set of that. That's Steve Mackay from Engineering Institute of Technology signing out of this presentation. Thank you very much for tuning in.